Hello scientists, this video I'm going to be reviewing the chemistry unit test concepts so that you can study for the big chemistry unit test we have coming up this week. What's going to be on the test? It's going to be all of these topics you see here, which I'm going to review one by one quickly. And for this video, I'm going to be telling you 4 secret words which you will have to submit for homework this week. Okay, so here we go. I'm going to begin with states of matter. States of matter, if you remember from a couple of weeks ago, is we have 3 forms or states or phases that matter can be in. As we know, matter can exist as a gas, it can exist as a liquid, or it can exist as a solid. Okay, we use our example of water because we have experienced and seen in our life water in solid form as ice, in liquid form as liquid water, and in a gas form as steam, okay, or as clouds. So as you know, in solids, the atoms are touching each other, they're closely locked in position, and they're jiggling, vibrating in place. In liquids, the atoms are more loosely connected. They're touching, but they're like sliding around each other. And that's what it means for something to be a liquid. In a gas, the atoms are not touching each other. They're very far apart from each other, and they're moving quickly, hitting each other, often once in a while. And that's what makes a gas a gas. And if you remember, gases have no fixed shape. Okay, I'm sorry. Gases have no fixed shape. They take the shape of their container. So if you put a bunch of steam, water, vapor inside of a jar, it's going to spread out and take the shape of the whole jar. Liquids also have no fixed shape. They don't keep a certain shape the way solids do. Liquid water, for example, if you pour it into a jar, will take the shape of the container as well. But a solid, as I mentioned, if we have a hard-boiled egg or an ice cube, those are solids. If you drop it into a jar, it's going to stay in the same shape as it was. It's not going to change the shape to fit the shape of the container that it's in. Okay, same thing. Not the same thing. It's a little bit different with volume. The volume of a solid is fixed. It's going to remain the same. You can't squeeze it to fit into a smaller space. The same thing with the liquid, right? Whether you pour a liquid Coca-Cola into a beaker that's like this or into a graduated cylinder that's this shape, it's going to have the same volume. It's going to still take up 355 milliliters of space. A gas, though, is the only one that does not have a fixed volume because you can squeeze down the gas molecules so that they do fit into a smaller space. Because there's so much space in between each of the atoms or molecules, you can squeeze that and compress the space. So you can get all of this gas. Let's say there's 1,000 atoms of oxygen gas in here and inside of the balloon at the surface. But if you swim down to the swimming pool all the way to the bottom, because of the pressure of the water surrounding the balloon, it's going to be squeezed down, but there's still going to be 1,000 atoms of oxygen in this balloon, even though they fit into a smaller amount of space. That's what we mean by saying that gases do not have a fixed volume. All right, so that's states of matter. I'm going to review now phase changes, which all can be summarized in this one diagram, okay? But first, let me tell you our first secret word. It's chick, okay? C-H-I-C-K, chick, like the little yellow chicken baby, okay? Chick. So for phase changes, you need to know that when we change phases from a solid to a liquid to a gas, we can go in 2 directions, right? You can get colder or hotter. Okay, so when you go from a solid to a liquid, are you cooling it down or heating it up? You're heating it up, right? Because you're turning all of these atoms that are locked in position, and now they're moving more and more because you're adding heat into the solid. So that's called melting. When you go the other way, when you get a liquid and you cool it down until it turns back, freezes back into a solid, that's called freezing. And from liquid to a gas, are you heating it up or are you cooling it down? You're heating it up, okay? The molecules are moving faster, just like we did in the gizmos. The liquid is evaporating into a gas, And when you go the reverse way, you're cooling a gas down and turning it back into a liquid. That's called condensation. All right. The difficult one are the two that are between solid and gas. So if you think about dry ice, we have a solid piece of dry ice, and then it's hot. Okay, so the atoms, they start moving so quickly that they turn right into a gas, skipping the liquid phase. That's called sublimation. And then if you go the reverse way, you take a gas and you super cool it real quickly so that it turns back into a solid. That's called deposition. All right, that's phase changes. Make sure you know that. Okay, next we're going to go and talk about atoms and molecules. And our second secret word is marshmallow, like the pink or yellow marshmallow birds that you get for Easter. Marshmallow. Okay, spelling doesn't count. You can spell it however. Atoms and molecules is next. So just to review, matter is anything that has mass and takes up space. I like to think of it as matter being made of atoms and molecules. Okay, so a baby, is it made of atoms and molecules? Yes, it most definitely is. Is steam made of atoms and molecules? Yes, it is. It's a gas form of water, still made of H2O molecules. Tables and chairs, yes, that's matter. It's made of atoms and molecules. Liquid water, rocks, flowers, cake, those are all matter because they're made of atoms and molecules. But there are some things in our universe that are not made of matter, or that are not considered to be matter. Heat is not made of atoms and molecules. Love, noises, light, those are not made of atoms and molecules. So it's not considered to be matter. Okay? Just the only thing you need to know for atoms and molecules is that molecules, like this big molecule of caffeine here, is made of atoms. Which one's smaller, molecules or atoms? It's atoms, because look at all of these atoms that make up the one molecule. Okay, we know our old friend, the water molecule, looks like a Mickey Mouse head, right? We got one big O, and it's connected to two H's. And we know that the water molecule is H2O, and it's made of 3 atoms. Okay, and look at this. This one's a carbon dioxide molecule made of 3 atoms, CO2. And then some of the other ones that we have discussed. Okay, that's all you really need to know about atoms and molecules. You need to know that atoms come together, stick together to create molecules. All right, that's all you need to know for that. Next up is properties of matter. There are a lot of properties, so make sure you study them. You got to know them all. We talked about before in class how all substances, all types of matter have unique properties that can help us to identify them. And when we did the gizmos, where you were a forensic scientist, you found some counterfeit coins, some fake coins. And how did you know they were fake? Well, we investigated the properties of those coins to know that, is it really made of gold? How do we know? We ran some tests on it. Okay, so we went over the different properties of various objects: gold, fool's gold, bananas, and eggs. We know that these are different from each other because they have different colors, textures, odors. And we also said that physical properties are characteristics of matter that we can observe without changing the identity of the substance. Okay, so look at this example here. If you have a bar of gold, or even if you smash that bar of gold over and over again and turn it into a super thin gold leaf, it's still gold. If you zoom in, it's still going to be made of gold atoms. Okay, we know that because it's a physical property. We did not have to change the identity of the substance to make that observation. Density is another physical property of matter. You can throw each of these different density cubes into water to see if it will float or not, to see how dense it is. And we know that the metal ones, copper, aluminum, those will sink in water. It's very dense. It's a lot of stuff packed into a certain amount of space. Even though every single one of these cubes takes up the same space, they're 1 inch by 1 inch by 1 inch, they all have the same volume. Well, they have different densities because of how tightly packed the atoms and molecules are inside. If we take any of these wooden ones, pine, poplar, or maple, they're going to float because they're less dense than water. Okay, so that's another property of matter that we can use to describe certain substances. Boiling and melting point, at what temperature does it boil or melt? We know that a clear liquid, if we boil it and it boils at exactly 100 degrees, that's when it turns from a liquid to a gas. We know it's water because that's the boiling point of water. And so different liquids have different boiling points because all substances, whether it's alcohol or water or gold, they all have unique properties. And boiling point is one of the properties that we know. Malleability, can it be shaped by hammering? That's another physical property of matter. Some things are malleable, like gold, like some metals, and some things are not malleable, like bone or like wood. It's not really malleable. And did we have to change the identity of the substance to see if it was malleable or not? No, you just changed it into a different shape, but it's still metal. It's still gold. Okay, solubility, that's another physical property of matter, whether things dissolve or not. And although the substance disappears in the water, as you remember from the Magic School Bus molecule episode, even though the sugar dissolves in the water, the sugar molecules are still there. So the identity of the substance did not change. That's why solubility is a physical property of matter. Conductivity is another one. Okay, you can use conductivity to describe. Metal is very conductive. Electricity runs through it very well. That's why wires are made of metal on the inside. But rubber, like these rubber gloves, are not conductive. That's why electricians use it when they do their work. For chemical properties of matter, you do need to change the identity of the substance to describe its chemical properties. For example, one of the chemical properties of matter is flammability. Some things burn and some things don't. And if we take a dry piece of wood and we burn it, well, once it's done burning, it's no longer going to be wood. The molecules are going to be totally changed to ashes and smoke. And so that's why it's considered a chemical property of matter, because we had to change its identity to figure out that, yes, it was flammable. Reactivity is another chemical property of matter. Does it react or not? If you mix salt and water and turn it into salt water, that's not a chemical reaction. It's just a physical change, because you can easily reverse that, right? You can evaporate all the water and the salt will remain. But if you mix baking soda and vinegar and it bubbles up into carbon dioxide, as we saw in our lab, you can't easily undo that reaction. These are reactive. They reacted with each other and formed a brand new substance. Okay, so that's it for properties of matter. And I'm going to talk about physical versus chemical changes now. Our third secret word is going to be egg, like an Easter egg that you can dip in different dyes to change the color, make different designs. All right, you do need to know the difference between physical and chemical changes. And if you remember, we compared them in a foldable. For a physical change, all we're doing is changing the appearance or the shape or the state of matter of a substance, and we're not making any new substance. It's still the same thing. Most of the time it's easily reversible, but not always. Okay, if you fold a piece of paper into a different shape, physical change. If you melt ice cubes into liquid water, that's a physical change. If you zoom in to the molecules inside of the ice cube or the water, it's still H2O. It's a physical change. Any kind of phase change is a physical change, like this water evaporating into steam. And bending a spoon, breaking glass, this is still metal. Even though you bent it, it's still glass, even though it has been shattered. It's just a physical change. Cutting hair, condensation, it's all a physical change. A chemical change, though, creates a new substance with different properties than what it had before. And they're not usually easily reversed. And oftentimes you'll observe signs of a chemical reaction, like heat being produced, or light being produced, or sound. Like what happens when you mix baking soda and vinegar. It'll bubble up, right? The temperature will change, if you remember from the lab, and it'll make a sound because of the bubbles. In orange molding, it's a totally new substance. It's not easily reversed. It's not reversible at all. That's totally a chemical change. Rust is a sign of a chemical change. And anytime you burn or toast anything like these marshmallows, that's a sign of a chemical change as well. So here are some other examples: wood burning, or anything burning for that matter. When you separate a water molecule H2O into just hydrogen and just oxygen, hydrogen, oxygen, those are new substances that are totally different from H2O. So that's a chemical change. Frying eggs or anything else, a permanent change in texture usually means you have chemical change. Anytime you see smoke forming, temperature change like the cold pack or hot pack, those are signs of a chemical change. Bubbles forming, like the Mentos and Coke experiment, that's a sign of a chemical change. A precipitate forming, rust forming. Anytime light is being created, like from the butt of a firefly or from candles burning, those are all signs of a chemical change. Changes in odor, like milk going bad, cake baking. Oh, that's permanent change in texture. Beans cooking, eggs cooking, or you eating a pizza. It goes through a chemical change in your digestive system as it's being broken down. Or a permanent change in color, like bananas ripening or meat cooking. Okay, that's the difference between physical and chemical changes. And our fourth and final secret word is basket. Basket. Okay, for endo and exothermic reactions, you have to know, let's summarize everything in this T-chart, okay? Everything is right here, and you can review your notes if you need more of a review. But basically, in exothermic reactions, heat gets released. And I remember that by looking at the EX, that's just like in the word exit. It means out. Heat is going out. That's different from endothermic reactions. En reminds me of the word enter. So heat is coming in. It's absorbing the heat. And so when you feel it, it feels cold because it's absorbing the heat. And in an exothermic reaction, that's like our NaCl example. When you combine sodium and chlorine, they combine to form a bond, and that releases heat. Bonds are formed. And for endothermic, I want you to think of the H2O being ripped apart into just H and just O. You're breaking the bonds right there, and that absorbs heat. Okay, so that's what we learned for endo and exothermic reactions. Now for chemical reactions, our final set of notes, you need to know that brand new substances are formed with different properties than the original substances. This is, the same stuff we were talking about for chemical and physical changes. For example, sodium, a flammable metal, chlorine, a poisonous gas. When they combine, they make a totally new substance with properties that are totally different from the original substances. And table salt, sodium chloride, is safe for us to eat. When chlorine and sodium, those are not really safe. Okay, so a reactant are the things that we call that we're mixing together. These are the things at the beginning of a chemical reaction. And what you get at the end of a chemical reaction is called a product. Okay, the products of a chemical reaction are what you get at the end. So that would be the NaCl, salt. And you got to know that whenever you see this arrow right here, that means a chemical reaction has taken place. The law of conservation of matter says that whenever we have a chemical reaction, you're not creating any brand new atoms and you're not ever destroying any atoms. That's impossible to do according to this law of conservation of matter. What's happening is during a chemical reaction is you're recombining or rearranging the atoms to make new substances. Okay, and that's what happens in a chemical reaction. So because of that law, because that law is true, that means on the reactant side of a chemical reaction, you need to have the same number of atoms of hydrogen as on the product side, 4 and 4. And same thing with the oxygens, 2 oxygens on the reactant side and 2 oxygens on the product side. All right, you've also got to know that a coefficient is the big number placed in front of a chemical symbol. It tells you how many molecules there are. So this big number right here means that there are 2 water molecules. And the little number is the subscript. I remember that because sub means under or below, like a submarine is below the water or a subway is below the ground. And you can see the little number is below all of the other symbols. And a subscript tells you how many atoms there are. So in an H2O molecule, there's 2 hydrogens, right? Those are the Mickey Mouse ears that are on top of the O, oxygen. All right, so you just got to know the difference between the coefficient big number and the little number subscript. All right, so that's the review. And let me know if you have any questions. Study a little every night. Good luck.